Okay. Just realized that my computer spit out the wrong set of notes, but we'll try to do this from memory mostly. So we're going to continue on with sort of our last discussion of scaling, and so this is going to be kind of the move from Chapter 6 into Chapter 7. I will post this afternoon. I'll post the schedule for the rest of Chapter 7, so you have the reading sections. So lecture 24 is going to be Scaling Concluded. So our topics are really going to be first what we call the scaling analogies. Correlation, and finally the introduction to what we call external flows. There we go. So, but before we get into that, quick recap, right? And this is sort of going to be our wrap-up of Chapter 6 up to this point. Okay. So we've said there are a series of governing equations, right? When we're dealing with convection, our governing equations are comprised of statements for mass conservation, energy conservation, momentum conservation, and so these three statements, right, really give rise to some more specific governing equations that we gave particular names. For example, right, momentum conservation, we'll start at the bottom and work up. Momentum conservation we stated using application of Newton's second law, and that led to the Navier-Stokes equations. Energy conservation, right, application of the first law of thermo led to this thing we call the energy equation. And mass conservation kind of gives us two different equations. One is the familiar continuity equation, but also gives us a equation called the species equation, which is basically conservation of mass when you have more than one type of material present. So things like mixing of two, as we call them, species of a solution in a liquid. And so with these three sets of equations, right, we set these up and we said, well, we haven't worked directly with the species equation, but I'll conclude with a few words on that. we said that between these three, there are very few problems where we can solve them exactly. So the next approach we took was to say we defined a series of characteristic quantities, as we called them. Those included things like the characteristic length, the free stream velocity, the surface temperature, the free stream temperature, the surface concentration, the free stream concentration, and I believe that's it for now. Right, and so we use these as a basis for our dimensions, and by non-dimensionalizing every term in the continuity equation, energy equation, and Navier-Stokes equations, we turned, right, these are all dimensional. We plugged them in here, and what we got out was a series of, make that black, a series of non-dimensional governing equations, right? And so this isn't like, you know, the utility of these governing equations is not terribly straightforward when you look at it like this. The advantage of going through this process where we simplified or plugged in, made these dimensionless, is that it makes those equations significantly simpler. The number of parameters involved in those equations ends up being in terms of dimensionless velocity, dimensionless temperature, dimensionless concentration. Fine, those are, you know, those are just non-dimensionalizations of what we were trying to find anyway. But like the coefficients in those equations, instead of being, you know, viscosity, density, the various terms that are scattered around there that are peculiar to a fluid, instead what came out was we generated a set of dimensionless parameters or groups, specifically things like the Reynolds number, which is equal to rho u infinity L over viscosity, right? The Prandtl number, I want to make sure I'm defining Prandtl number correctly here. Oops. Prandtl number, which is the thermal capacity, mu over K, right? The Eckert number, it's equal to u infinity squared over C times T infinity, or Ts minus T infinity. And the Schmidt number, which is the kinematic viscosity, or the kinematic viscosity over the mass diffusivity. And so, right, this set of four parameters are what we end up seeing alongside our dimensionless velocity, dimensionless temperature, and dimensionless concentration. So to kind of wrap up what that does for us is we can we've established that it's really hard to solve those equations directly. And so what this non-dimensionalization allows us to do is say, okay, I'm going to look at this equation, I'm going to look at the terms involved, and I'm going to say, based on the way that equation is formed, which of these parameters do I think affect the solution of interest? So the way this goes is if we say the momentum equation, for example, the energy equation, and the species equation. So let's say these are our three important equations. We'll leave continuity out of here because that just sort of is a addition to each of these. So we can separate it into these three sort of types of equations. What are we trying to get out of each of these? Like, what is our solution of interest if we were able to solve these? Okay. Well, in the case of momentum, right, dimensionless momentum, we'd be solving for u star, right, which is the dimensionless velocity. For energy, we'd be solving for theta star, which is the dimensionless temperature. And for the species equation, we'd be solving for C A star, the dimensionless concentration. And if we looked back at each of those equations, what we would find is, and this is where I need to consult the notes, that we could, for example, for the momentum equation, we would say, all right, the momentum equation is going to be a function of for example, x star, y star, so the location in a flow, the Reynolds number, and the dimensionless pressure gradient. Okay. The energy equation contains similarly x star, y star, but Reynolds number, also the Prandtl number, and dp star, the dimensionless pressure gradient. And the species equation is going to involve, let me make sure I got this right. Actually, I forgot the Eckert number in here. And the species equation is going to be a function of, once again, x star, y star. Reynolds number, the Schmidt number, and the dimensionless pressure gradient. So what this is saying is if we were to solve these, right, this isn't saying we know the solution. We're just saying that if we were to modify any one of these particular variables in the governing equation, we would expect it to affect this solution. Okay. Okay, so if we were to, for example, then take each of these quantities, right? This is if this is the dimensionless velocity, dimensionless temperature, and dimensionless concentration, what we're also interested in, right? The thing that we're generally looking for in this chapter is how quickly, for example, we're focusing in on this one, how quickly we are dumping thermal energy into a flow. Okay, so that's going to be a function of the temperature, namely through the use of, right, we define this thing called the Nusselt number, which is defined as HL over the fluid conductivity, which is also defined as the dimensionless rate of change of the temperature at the surface. Okay. And so if the Nusselt number is dependent on this at some value, then we can go ahead and say that the Nusselt number, by extension, just by looking at this, is going to be some function then of x star, Reynolds number, Prandtl number, Eckert number, P. Okay, so this is our sort of our dimensionless version of the heat of the convection coefficient. Momentum has a similar thing going on, right? Rather than, so if you're considering velocity, instead of like the transfer of thermal energy, if we consider this to be the transfer of momentum, right? The rate at which momentum is transferred from a surface to a fluid. What that leads to is, right, rate of change of momentum is equal to a force, right? It's Newton's second law, F equals ma. And so that gives us, if we non-dimensionalize that, what we get is what's known as the friction coefficient, Cf, which is equal to basically the force due to friction, or we'll go ahead and, instead of saying force due to friction, we'll say the shear stress due to friction divided by 1/2 rho u infinity squared, which is equal to viscosity times du dy at y equals 0 over 1/2 rho u infinity squared. And so what we've got here is, right, u sort of finding its way into solution. If we were to non-dimensionalize this, it becomes 1 over, you know what, in the interest of avoiding writing something incorrectly, I'm just going to leave it there. But right, we see that because the velocity finds its way in here, then we can go ahead and say, well, if it's dependent on the velocity, it'll be dependent on the non-dimensional velocity, and therefore x, Reynolds number, dp dx are going to find their way in there. We get rid of the y because we're evaluating at this some known value of y equals 0. So we can say that then Cf is equal to a function of x star, Reynolds number, dimensionless pressure gradient. And finally, for the species equation, right, we end up with a similar thing going on. The species equation looks a lot like the energy equation or the Navier-Stokes equations. Once you non-dimensionalize it, just has some different parameters in there. Namely, instead of the Prandtl number, it's got this SC, the Schmidt number, and we've gone ahead and dropped this Eckert number out of the dependency. So how do we describe the sort of the rate of species or concentration being transferred between a surface and a flow? For example, wind flowing over a river. How quickly is water vapor being dumped into the air by the action of evaporation? That's the sort of analogous to the convective heat transfer rate, right? But it's the convective mass transfer rate. So instead of the Nusselt number, we define this thing called the Sherwood number, SH, which is defined as HM, where that means mass convection heat, the mass convective coefficient, L over dA. So dA there is the mass conductivity or the mass diffusivity. And the Sherwood number then is defined as a function of, once again, x, Reynolds number, the Schmidt number, and dp dx. This probably seems really abstract right now. This doesn't have a whole lot of meaning to you, I'm guessing. But hopefully by the end of the lecture we'll see at least why this is a really useful sort of functional relationship to write. Okay, one last little manipulation we're going to do here. Notice that this dp dx finds its way into each term. The non-dimensional pressure gradient is, right, that's basically a function of the way that a flow moves around some object, which means it's a function of the geometry of the object. So if we're dealing with, for example, flow past a flat plate, which is one of the kind of problems we're going to be coming back to a lot. If the pressure isn't changing along the length of that flat plate, then this goes to 0. Similarly, if we're saying we want to evaluate the way that the friction coefficient, Nusselt number, and Sherwood number vary over a known geometry, right? Something where I'm not changing the pressure gradient, then you can eliminate this because you're essentially saying it's going to be constant for all values. So for now, we're going to go ahead and strike the non-dimensional pressure gradient, we're going to be looking at flat plates mostly where there is no pressure gradient. Okay, next thing to consider is, right, these are all what are known as local quantities, meaning that they depend on the location at which they're being measured. All right. If we wanted to define a average quantities, remember we talked about there's a difference between a local convection coefficient and an average convection coefficient, H versus H bar. We could go ahead and define an average of this quantity over the entire surface area that we're considering, basically over all values of x. So if we do that, we get what's known as the drag coefficient, and this is basically the average of the friction coefficient, which is simply a function of Reynolds number. Okay, so what this means is if you were to take a flat plate, put it into a moving fluid, okay, and you were to measure the shear stress at a point, non-dimensionalizing that shear stress gives you the friction coefficient. If you were to measure the entire drag on that plate, right, how much force is being exerted on it by the flowing fluid, and you were to non-dimensionalize that, then you'd get the drag coefficient. Okay, so that's no longer a function of the location on the plate, that's a function of the whole plate taken as a whole. Similar thing for the energy equation. All right, if we're talking about heat transfer, this version of the Nusselt number is going to tell you what the convective heat transfer coefficient is non-dimensionalized at a point. If you wanted to take that, find a non-dimensionalization of that H bar term, then you end up with Nusselt number with an over bar, and we, because we're averaging over x, get to drop the x star term. Last, another thing I should mention is that the Eckert number here, for most of the flows we're going to be considering, this is really small. And so to keep things simple, for now, we're going to go ahead and cancel this out, but I'm going to put a question mark, meaning this is something we're not going to be able to do all the time. But for the purposes of this class, I don't think we're going to be doing anything with significantly large Eckert numbers. So Reynolds number, Prandtl number, and if we leave out the Eckert number and the pressure gradient, we end up with this relationship. And finally, same thing with Sherwood number. Okay. Again, that example of wind flowing over the surface of a river or lake. If you were to measure the sort of the flux of mass at a point and get that mass convection coefficient, H sub m, at that point, fine. Right, that's your local value, but if you wanted to figure out how much mass is being transferred from the entire surface of that body of water, then the corresponding mass transfer coefficient is going to be SH bar equals HM bar L over dA. It's going to be a function of just Reynolds number and Schmidt number. So these are the things that you want to know, okay? And these are the things that we're going to keep coming back to. But now, hopefully, you're starting to see why this is a useful way to write kind of the behavior of our convection coefficient, right? If it's really hard to solve the problem directly, then this sort of assumption means that, just like in fluids, we basically boil down the number of parameters of interest from 8 or 9 to 2. And so it would be really easy, for example, to run a series of experiments, do some curve fitting, and figure out sort of an approximate functional dependence that you could then use to get Nusselt number. And if you know the fluid conductivity and you know your characteristic length, which you should because you picked it, then you can solve for H or H bar, depending on which one you're interested in. We'll do a little more on that later. But for now, let's talk about how we can use this more directly. For example, if we were to take a known geometry, and this is quick example here. Let me give a moment to sort out. Okay. I guess before we move on, is anybody dare ask any questions right now? Should we just keep going and see what questions come up? All right. So example, this is from the book. This is problem 624. Let's imagine that you've got a turbine blade, right? For example, in a steam or gas turbine. Okay, here's a turbine blade. It has flow moving past it at T infinity is equal to 35 degrees Celsius. Okay, and U infinity is equal to 100 meters per second. Let's say that this thing has a length, right, of 0.15 meters. That's basically defined from the nose to the tail. The entire surface of this thing is at some temperature 300 degrees Celsius. So, for example, this might be a turbine blade that's being subjected to a cooling flow. And so let's say a series of experiments have been run on this, and what we've found is that the total heat transfer out of this blade into the moving air is Q equals 1,500 watts. Let me move some stuff around here so it's a little less cluttered. Oh, or delete it. Okay, so this is the total rate of heat transfer from the blade to the air. All right. Now let's say that someone, right, a company that's building these things decides, I want my turbine blade, or I want to design a turbine blade for a slightly different application. This other turbine blade is going to be, pretend that these are the same shape. I'm not. I'm gonna scale this turbine blade up. It's gonna have an identical shape, but this one is going to have a length of 0.3 meters. We're also going to run it at a higher temperature. This is going to have a surface temperature of 400 degrees Celsius. And we're going to put it into a stream of air that has a velocity of 50 meters per second instead of 100. But that stream of air is also going to be at it's going to also be at 35 degrees Celsius. Okay. So the question is, what is going to be the total heat transfer? Oops. What is going to be the total heat transfer rate out of this larger modified blade? So, right, this kind of problem, if we wanted to try solving it using the direct application of the energy equation and Navier-Stokes, we're out of luck. We're totally unapproachable using the straight math. Okay, you could do simulations, right? You could plug it in, brute force it using some sort of simulation code, but there's a much more elegant way of solving it, a much more elegant, easy, and faster way of solving it if we use a few assumptions. So the assumptions here, we're going to assume that this is steady state. As usual, we're going to say that both blades are of the same material. And are operating in the same fluid. And we're going to say that the surface area of the blades is proportional to L. In other words, let's say it's this one's 1 meter into the page. That one over there is also going to be 1 meter into the page. So the surface area scale with however much we increase the length. And then finally, I already stated this one, but we're assuming that the two are geometrically similar. So they have the same shape. All right, so how would we proceed here? Well, if we scroll up by about an inch here, we're going to go ahead and take advantage of this relationship, right, that we developed for the Nusselt number. Okay, the Nusselt number is our dimensionless convective heat transfer coefficient. And it's dependent on only these two parameters, Reynolds number and Prandtl number. So let's go ahead and compute the values of the Reynolds number and the Prandtl number for each of these two cases and see if we can learn anything. So we know that, right, the mean Nusselt number, which is h bar L over kf, is a function of Reynolds number and the Prandtl number. So Reynolds number, Prandtl number, let's say for blade number 1, blade number 2. So we'll make a little table here. So Reynolds number for blade 1 is going to be U infinity times 1 times L1 rho 1 over mu 1, and the Prandtl number for blade 1, erase that, it's going to be Cp1 mu 1 over K1. Reynolds number for blade 2, similar, U infinity 2 L2 rho 2 over mu 2, and Prandtl number Cp2 mu 2 over K2. So from up here, right, we can make a couple of assumptions about, for example, the velocity, the length, the density, etc. Of these quantities respectively on blades 1 and 2. For example, if we number these assumptions, right, if we say 1, 2, 3, 4, then from assumption 2, okay, both blades are of the same material, operating in the same fluid. That means that all of our fluid properties, for example, density and viscosity, as well as our solid properties, for example, K, those are equal in both cases. Okay. So we can go ahead and right here that then this is equal to right, rho 1 mu 1 U1, K1. For blade number 2, said that U infinity, scroll up, is half of the case of blade number 1, and that the length is double. So we end up with U infinity 1 over 2 times 2L1. And those 1 over 2 and that times 2 cancel out. For Prandtl number, the CP is going to remain constant as well, because that's a fluid property. And so what we end up with is that if we compare, right, U infinity 1, L1, rho 1 over mu 1, U infinity 1, L1, rho 1 over U1, mu 1, etc. The Reynolds numbers and the Prandtl numbers are the same in both cases. Reynolds number 1 equals Reynolds number 2, and Prandtl number 1 equals Prandtl number 2. So these two considerations taken together, right, if we look up here, we say if the Nusselt number is a function only of the Reynolds number and the Prandtl number, and if those two quantities are held the same, then the Nusselt number also has to be the same. Nusselt number 1 has to equal Nusselt number 2. All right, so the next step here is to write this out as, right, if the Nusselt number is defined as h bar 1 L1 over KF1, and this is equal then to h bar 2 L2 over KF2. We've already said that, right, KF1 and KF2 are the same, so we can go ahead and get rid of those subscripts and just leave it as KF, which is constant. And so we can solve for h bar 2, which is equal to h bar 1 times L1 over L2. Finally, right, we don't actually know what h bar 1 is, right? We know only how to write it in terms of one of our rate equations. So we know that for blade 1, right, Q1 is equal to 1500 watts. If we plugged in Newton's law of cooling, we say that that's equal to h bar 1 times A1 times TS1 minus T infinity. If we go ahead and solve for H1, h bar 1 from that, h bar 1 is then equal to 1500, well, we'll write it symbolically first, Q1 over A1 TS1 minus T infinity. And we can say that if we plug this in right here, we can write, I drew an arrow to the wrong place, right here. Okay, then we can say that h bar 2 is equal to Q1 A1 TS1 minus T infinity times L1 over L2. And finally, one last step. So what we're looking for is Q2, right? So just like we use Newton's law of cooling up here to back H1 out from Q1, if we're looking for Q2, let's just run it the other way. So we can say now that Q2 is equal to h bar 2 times A2 times TS2 minus T infinity, and substitute this in for h bar 2. So this ends up being Q1 times A2 over A1 times L1 over L2 TS2 minus T infinity over TS1 minus T infinity. So if we look back at now our assumption number 3, right, surface area of the blades is proportional to L, then that means that A2 over A1 is proportional or is equal to L2 over L1, which cancels out the L1 over L2 right next to it. And if we plug in our numbers, right, so this ends up being 1500 watts times 400 degrees Celsius minus 35 degrees Celsius over, was it 300 or 350? 300 degrees Celsius minus 35 degrees Celsius. This ends up being a value of 2066 watts. Okay. So what that's doing down there. So despite the fact that looked like a lot of stuff we just did, we need to understand how simple that process really was. We said we have flow around one object. If we identify that the Reynolds number and the Prandtl number for that object are equivalent to another object, what we've done is we basically created what's known as a scaled model, right? We did this in fluids, where you say all you have to do is reproduce the same, maintain similarity of those dimensionless parameters, and your dependent dimensionless parameter, in this case the Nusselt number, will also then be the same. Okay? And so then once we knew the Nusselt number relative to another value, we were able to redimensionalize that to actually get H, or H bar, and rescale the smaller blade to get a new heat transfer rate out. So, like I said, this is a case of sort of a direct scaling approach. What we didn't do here, right, is really break out that much math in terms of solving any equations. This was just substituting stuff in. And we could substitute all day long. What if we don't have a scale model, though? Right? Well, then, just as I mentioned before, the approach, if you don't have a scaled model and you can't do this direct scaling, where you just get the value of the Nusselt number from something else, then the approach you have to turn to then is, oh my gosh, come on. My computer's done. All right, is what's known as correlation. And so, speaking very generally, we only have a couple minutes, which is fine because this is a quick little overview. The idea with correlation is you can go through and you can systematically vary the Reynolds number and the Prandtl number and measure, for example, measure the values of the Nusselt number and create sort of a database and do some curve fitting. So, for example, let's consider the flow past this flat plate, right, which has length L. And through this flat plate, we have run a sort of a heating wire, okay? And past this flat plate, we are measuring, we have some flow, U at some speed, U infinity, and some temperature, T infinity. So the equipment that we've got on hand, we'll say, is going to be this resistance wire with some power meter, so we can basically measure how much energy per unit time we're dumping into this heating wire. And we have two temperature probes, one on the surface and one out here in the free stream. So two temperature probes. So what we might do is set the flow at some, U infinity, T infinity, just get the flow going, and start to gradually increase the amount of power that we're applying to this heating element in the plate until we end up with the surface temperature being hotter than the fluid temperature. Okay, when that occurs, then we know we're transferring thermal energy into the flowing fluid. Okay, so there's convection taking place into the fluid above. We're going to go ahead and assume that like the sides and bottom of this plate are adiabatic. Okay, so this is a case where flow is only occurring out through the upper surface. So if we measure, right, the amount of power used to generate heat, then this is effectively this is our Q, right? Our rate of thermal energy transfer to the fluid, which is equal to h bar times the surface area of the plate times Ts minus T infinity, where those quantities are being measured by these two temperature probes, Ts and T infinity. So we can say h bar then is equal to P, the heater, divided by the surface area of the plate times Ts minus T infinity. Right, so measured by our power meter, measured by our two temperature probes, and we could non-dimensionalize that as the Nusselt number, h bar over, or times L over the conductivity of the fluid. Okay, so what we've done is basically we've set up the flow in one way, and we have measured the Nusselt number. If we were to vary the velocity of the flow, right, change U infinity, then we are changing the value of the Reynolds number. Okay, so if we were to systematically vary U infinity, we'd go ahead and collect the Nusselt number for a range of different Reynolds number values. Vary U infinity to vary the Reynolds number, and once we're done changing the Reynolds number, we could, for example, swap out the type of fluid we're using. So maybe we would go from air to water or to engine oil. And when we do that, we could then vary the velocities all over again to do this sort of sweep with different values. Change type of fluid and repeat test to vary both the Prandtl number and the Reynolds number. Because as soon as you change the fluid, you're going to have a totally different value of the Prandtl number. And you can continue to do this. Change the velocity and the type of fluid you're using systematically to basically create a database of Nusselt numbers as a function of a wide range of Prandtl numbers and Reynolds numbers. So that pretty much wraps up what we're going to do. I guess the motivation is that for the remainder of this chapter, or chapter 7, and the rest of the course, it is we're going to be taking advantage of the fact that people have done experiments like this for 100 years and created these sort of correlations and these curve fits that you can use to look up Nusselt numbers based on Reynolds numbers and Prandtl numbers. And from that, you'll be able to get heat transfer coefficients and actually get wattages. So we'll pick this back up on Monday.